Hi guys, here's our gravitation notes. It's a big piece of this circular motion idea, and we include it here because obviously the planets move in circular orbits. They're actually not quite completely circular. They're a little bit elliptical. We can talk about that a little later. But remember, in physics, we like to use simple models to try to make sure we understand the things. So I'm going to basically just kind of jump into the mathy stuff, but I do want to talk about this big equation first. We have a new equation to talk about the force of gravity. And it used to be, every time we talk about the force of gravity, we were basically just saying mg, right? And it was the mass of the object times 9.8. And that was the force of gravity that was provided on a beam, providing torque, providing friction, all that kind of stuff. But now we have a new force of gravity, and it's this big equation here. Big G is a gravitational constant, and we have its value here. This G is equal to 6.67. We usually use the 6.67 version. But 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And so most of the time we just end up writing the numbers. But big G is the gravitational constant. M1 and M2 are the masses of the object. And so basically, in a nutshell, anything that has mass creates gravity. So the Earth creates gravity that brings us to the Earth. We actually have gravity that brings the Earth to us. The sun and the solar system has gravity, and it gets bigger and bigger and bigger. So basically, anything that has mass has gravity. The R is the distance between the centers of masses, and that's important because sometimes we can have a question that gives us the orbital radius. Anytime it says orbital radius, it means that big distance there. I could ask how high above Earth, right? And so basically it's going to be the orbital radius minus the Earth radius, and that would give us how high above the Earth is. So we'll just, make sure we understand what the question is asking us. But the first few are fairly straightforward. Let's go ahead and jump into this. So we have our first example here. We have the force of gravity between two 75 kilogram students if their centers of mass are 0.95 meters apart. All right, so let's go ahead and do a couple of things first. Let's write our equation that we're going to be using. It'll be Fg is equal to big G m1 m2 over r squared. And we know, we have the two masses are 75 kilograms. So let's write off to the side real quick what I know. I know each mass is 75 kilograms. So kg, so make sure I know what the masses are. The radius, so this case, the centers of mass, it gave it pretty straightforward there. So it's 0.95 meters. And we're looking for the Fg. And we know the given big G is that 6.67 times 10 to the negative 11th number. So let's go ahead and plug everything in here. We have big G is, that's 6.67 times 10 to the negative 11th number. And then you can do 75 squared or just plug it in. So first time we've done it, we'll just plug them in. Divided by r squared, so 0.95 squared. When I plug in all these numbers, I get this really small value of 4.157 times 10 to the negative 7th newtons. This is a tiny force. So in general, gravity is a pretty weak force. Fundamentally, it's a pretty weak force. We'll talk a little bit later on, a little bit next week, about how black holes work and gravity actually becomes super, super strong, and there's a little bit of math background that we'll do. But basically, it's a very tiny force. So gravitation is kind of a weak thing, but it's kind of cool too at the same time. that weak force is what holds our big solar system together. That's kind of cool. Here's a kind of an interesting question here. Sometimes we ask you to figure out the ratios of things. Basically, we have a satellite here that weighs 9,000 newtons on Earth's surface. And how much does it weigh if we're going to triple its mass and then double the orbital radius? So here's how we attack this kind of questions. Here's how we approach it. We know that the force of gravity is big G, M, and I'm going to do this way. On purpose, I wrote a big M and a little m. Okay? What I'm talking about here is when we have these kinds of questions, we're looking at the big M as being the gravity-producing thing. So in this case, it'd be the Earth. And then the little mass would be the thing circling the gravity-producing thing. So like a satellite or something like that, okay? What it's telling me, though, is that we're going to triple its mass, okay? So I have Fg, that big G stays the same. But what I'm doing is I'm getting my little m, and I'm tripling that. The mass of the Earth remains the same. And down here, what I've done is I said I also doubled the radius. So it looks like that on purpose. Right, when I plug these numbers in, I get something that kind of looks like this. I get this 3/4 number, and the rest just stays the same. Big M, little m, over r squared. So notice I have this 3/4 thing. So when you have these kinds of questions, all you're going to do is going to get this 9,000 over here, multiply it by 3/4, and we get this, I'm going to say Fg sub nu, kind of a funny way to write that, but we get 6750 newtons is how much something would weigh if it was a far off distance, or I've doubled and tripled the mass and that kind of thing, okay? All right, so let's just take, basically, it's if we look at this first page here, we have this idea that this cannonball is being shot. If it's not shot fast enough, it falls into the Earth, right? And then the one that going around the circle, around the Earth, it looks like it was shot just fast enough to keep going around. If it's shot too fast, right, that means it would fly away and not orbit the Earth, right? So what we end up talking, the next kind of question we'll see here, we have what mass must be located at the sun's surface. So what we're doing is we're looking at this theoretical idea here, is we have the sun, and an object is sitting on the surface, and we're trying to figure out what the Fg is here, okay? I'm sorry, we're trying to figure out what mass causes that. So here's how we do this. Again, we have this Fg equals big G, little m, big M over r squared. And what we're going to be looking for is the little m here, like what mass that we're going to do. So the way it's defined is it looks like it's given us all this information. So I'm going to go ahead and plug everything in here. Looks like Fg is 470. The big G is that 6.67 number. Looks like I have the two masses. So I'm going to use my big M here as the 2.0 times 10 to the 30 kilograms, the mass of the sun. And looking for that little mass, what is on the surface of the sun. And then here, it looks like the radius that we'd be given, right? That's going to be the radius of the sun there. So we can go ahead and use this 7.0 times 10 to the third kilometers. Remember, this has to be in meters. This is actually 7.0 times 10 to the sixth meters. So make sure we pay attention to the units that we're using. So down here we have 7.0 times 10 to the sixth. And remember, it's r squared, so I have to square that. A lot of the errors I see tend to be centered around this thing right here, making sure we're squaring that when appropriate, okay? So we do a little bit of math, and so one of the things I want you guys to do is make sure do the calculator steps to get this. but we get a little mass value of 1.72 times 10 to the negative fourth kilograms. Well, when you think about it, this is 0.172-ish grams. This is a really small mass. So what that tells us is the sun must have a really big gravitational pull on the surface, right? When we think about it, this 470 Newton weight on Earth would be kind of close to about 100 pounds, okay? So on Earth, if I hold 100 pounds, that's kind of what we're dealing with, that force. What this is telling me is that this 0.1, this is less than a gram. Maybe it's like a paper clip. On the surface of the sun, that paper clip would weigh close to 100 pounds, right? So that's just telling you how strong that gravitational force is on the surface of the sun because it's so massive. Here we're looking for how far apart. So what we're looking for is we're still using our gravity formula here, big G, 2 m's, and on this case, we have this 2 masses, so I don't necessarily need to write like a big M to say it's talking about like a gravitational body or anything like that. Sometimes we can just say M1, M2, so we have a little bit of interpretation there as we look for that. But we're looking for the R squared here. So it looks like I have enough information. I can kind of just fill this in. 3.0 times 10 to the negative 6th. So all I'm doing is plugging stuff in and figuring out what to do after I have things set up to do the algebra for it. So it looks like what happens is I'm solving for this R squared down here. So I end up doing something like this. And once again, make sure your calculators are up to speed here. So we get 0.667 meters, how far apart those things are, okay? So just make sure we can get there and we're comfortable doing that kind of thing. All right, so we have one last topic to look at, and this deals directly with what we were talking about in terms of circular motion when we first started talking about that. When a satellite is in orbit, what's happening is it's going just fast enough that it's going around the sun. About is understanding that there's this weightless idea. And if we remember back to that vertical circle, this is basically a big fancy minimum speed question. And when we talk about minimum speed, we end up saying that the centripetal force of the object is equal to the Fg. And so when we're talking about tensions and all that, we knew here Fg was mg. Well, now we have something else that's providing that gravitational force. We have this big Fg equals big G mm over r squared idea. So what happens is this gravitational force idea now becomes the big equation. So when I take a look at this, I can do a couple of things. The first thing I'm going to do is I'm going to look at the centripetal force and understand that it's ma sub c. That's the centripetal force there. Well, then this new way to write Fg is now big G times big M little m over r squared. So since we're talking about something falling around the Earth is the gravitational body, so I like to say there's that big M. That's what's causing that gravitation. So we have one more way to describe the centripetal acceleration here. This turns into mv squared over r, and we got pretty good at doing those questions. This is big G m big M over r squared. Okay, so it looks like we have enough information here. There's several things we can do here. Certain things can cancel, so if I look at it here, I'm not going to do it all the way here, but these m's end up canceling depending on what's going on. So it looks like it's just the gravitation of the planet causing the thing to circle. There's lots of different things you can do. But the ultimate thing that I want us to understand is that this relationship right here is what's going on because it's a minimum speed idea. Okay, so what kind of question can we ask her about that? So here's what we have, right? We have a satellite traveling around. So it's basically, if it goes any faster, it goes away. If it goes any slower, it falls into the planet. All right. So we have this idea, at what speed does it travel, which means that the centripetal force must equal the gravitational force. Cool. Well, I'm going to go ahead and jump to this form of the equation down here, to where I'm going to say it's mv squared over r is equal to big G little m big M over r squared. We're using this m as the mass of the Earth, and the mass of the Earth happens to be about 6.0 times 10 to the 24th kilograms. And once again, we're looking for the speed that the object is traveling. And so when I'm looking at my equation, the only place I see speed is right here in the centripetal force idea. Here, it looks like the masses end up canceling, and we're talking about the little m here cancels across the equation. So I can rewrite that to say v squared over r is equal to big G big M over r squared. And if we're pretty good at math, and I hope we are, we look at this and say one of these r's can cancel. Very cool. So I end up with this idea of v squared equals big G big M over r. And so I take the square root of that. And there's the mathy version of the answer there. To get how fast we go, we can just plug stuff in. 6.67 times 10 to the negative 11th. Mass of the Earth is 6 times 10 to the 24th. The radius that we're looking at is this orbital radius. So it's this 8.5 number. And I take the square root of all that, and I should get a speed of about 2169 meters per second. So he's moving pretty fast to keep going around the Earth like that. All right, so there's our gravitation in a nutshell, okay? I'll be back on Tuesday, and so instead of a mini quiz in the beginning of class, we're going to go over a couple of things and start a centripetal force, centripetal motion lab, basically. And then we will discuss a little bit further what the rest of the looks like. All right, guys, thanks for watching. Bye.